So, very warm welcome to everyone for this session of the Proteus seminar series. We have today two speakers. I'm very pleased to introduce you Olimpia Lombardi and Cristian Lopez. They will be talking about a topic that is, of course, close to the close and at the heart of the project, a cosmological geometric approach to the arrow of time. So Olimpia and Cristian, thank you very much for being here, and I leave it to you.
Okay, first of all, thank you, Sylvia, for inviting us. Thank you, everyone, for being here, at least virtually. On my behalf, and I think Olympia's behalf, it's really a pleasure for us to discuss our ideas and project with you. So, second, this presentation that we'd like to discuss with you all is based on a project that now we are running in our group in Argentina, funded by the John Templeton Foundation. So it's a we just started this project. It's about the arrow of time and the arrow of time in a cosmological model, in a cosmological context. So now what we are going to present are some ideas that we have in order to develop our project. Some of these ideas were already published by Olimpia and Castanino. That was a former collaborator of Olimpia. But now the idea is to develop this approach further, to fix what needs to be fixed and to expand it as we can. And that's why it would be very, very useful for us to have your feedback, your criticism, your objection, everything that you want to say about what we are going to discuss. It would be very helpful for us because it's part of the project that we are running now. So let's get started with this. Well, the title is the one that Sylvia already said. Our starting point is the following. We want to defend the following simple claim. We live in a universe with a direction of time, right? This direction of time, we will claim, is primitive and holds for the entire universe. This is the first simple claim that we are going to defend. And the proposal will basically be that the arrow of time is an intrinsic geometrical feature of space-time. For us, and the idea that we have in mind is that it just happens that our universe comes equipped with an arrow of time. Our universe just meets the right sort of structure to support an arrow of time. This is the goal of our project. We want to develop a philosophical approach to the arrow of time that meets this simple and I think strong claims about the arrow of time in physics. Now we have to give some introduction about the discussion of the arrow of time that is already a bit messy, and then we are going to develop our approach. So this is roughly the map of the talk. First, I will try to formulate in a clear possible way what is the problem of the arrow of time. This is already a problem because different people understand the problem differently, and it's not easy to find a common ground to discuss the topic. So I would try to make some effort to lay this basis of understanding. Second, I would just briefly discuss some approaches, some general approaches like the difference between global and local arrow of time, why we like to go with a global arrow of time, and then discuss the two different philosophical approaches like the reductionist approach and the primitivist approach, and why we will support a primitivist-like approach to the arrow of time. And then the basics of our project. This is the last part and the substantial part, and where we like to hear your feedback and comments. So let's go to the first point. As I said before, I mean, it's already problematic to define what is really the problem of the error of time. Almost 50 years ago, John Ehrman already warned about this issue, saying that it seems not a very great exaggeration to say that the main problem with the problem of the direction of time is to figure out exactly what the problem is or is supposed to be. And when one is running through the literature about the error of time, it's quite evident that people usually discuss different topics under the same level. And okay, so these are already a problem. So to show that these differences, let's say that, for example, some people think that the error of time is mainly about the nature of entropy increases processes or irreversible processes. This is, for example, Reichenbach's branching system, or, for example, David Albert and Barry Lower's mentaculous approach. They think that the nature of the error of time must be somehow given by explaining the nature of entropy increasing processes. So when we are discussing the error of time, we are also discussing the nature of entropy increasing processes. Some other people think that, more or less in the same line, that the real issue with error of time is the problem of time reversal invariant laws. For example, in this case, Paul Orwich, in a famous book in the 1987, he rejects that there is an error of time in our universe because the underlying laws are time reversal invariant. Then other people think that there is an error of time in our world because the violation of CPT in weak interactions in quantum field theory, for example, the decay of chaos or meson B's or whatever. But again, I mean, some people think that it's about entropy increasing behavior. Other people think that it's the enterprise to find non-time reversal invariant laws. And the discussion is not exactly the same. They could be somehow related each other, but it's not exactly the same. But again, this just is adding more complexity in the discussion. Other people think that the discussion about the error of time is mainly about the relation between thermodynamics and the underlying classical mechanics. This is probably the orthodox approach is related to the first point I mentioned just before, but the main issue is try to figure out how can we explain the evident time asymmetry of, for example, entropy increasing processes, but could be also other asymmetric processes if the underlying physics, in this case, the underlying classical mechanics, is time reversal invariant. And this is the discussion. This is the orthodox view in the error of time, how usually the problem is posed in many textbooks or many papers or in many approaches to the error of time. For example, this has an origin in Loschmidt paradox, for example, and Boltzmann replied to the paradox, and so on and so forth. But again, everything is related. Now we have, again, time reversal invariant laws, also thermodynamics, but now it's the relation between these two concepts. So again, this adding more complexity to the discussion, but also it's not quite the same discussion. But everything is discussed under the label of the error of time. Other people have posed the problem now in terms of finding special conditions or postulating special conditions at the beginning of the universe, for example. This is, for example, the Boltzmann replies to Loschmidt paradox with this one asymmetry model, but also is the Albert's idea with the past hypothesis. So the solution of the error of time, of the problem of the error of time, is to try to find if we can obtain some particular asymmetry between initial and final conditions. For example, this is the role that the past hypothesis has played in the discussion. Now, if we move on to the cosmological model, and again, now the problem usually is is accounted for in terms of whether there is an asymmetry between initial and final condition of the universe as a whole. And then we have a bunch of different models like Gold's universe, where there are initial and final conditions that are symmetric. Therefore, there would be an arrow of time, or Penrose's Big Bang and Big Crunch model, where there is an asymmetry between initial and final condition. Therefore, we can define an arrow of time in terms of this asymmetry, or Gödel's universe with non-objective temporal lapses, so closed temporal curves, therefore no arrow of time. Again, everything is discussed under the same label, the arrow of time, but the particular aspect of these issues are different and demands different approaches. But again, the problem seems to be everything of all of these, but nothing particularly related to this particular with any of these issues. So we can just put all these approaches aside and start to think the problem all over again from the beginning, from a more philosophical, maybe a more philosophical approach. We can say, well, I mean, at the end, the question is about whether time has a direction according to our physics, if we want to defend a more physicalist or naturalist approach to the arrow of time. So we can think that the enterprise to solve the problem of the arrow of time is to find a substantial difference between different sort of temporal series. And this is very helpful to rely on McTaggart's formulation of different temporal structures. If you remember, McTaggart proposes that there are three kind of temporal series: the A series, the B series, and the C series, instantiating different structures. But in these particular cases, when we are asking for the direction of time, we are asking whether time has, according to physics, a B structure. A B structure is one in which we can define earlier than and later than relationships. So then, okay, there is some discussion whether the A series is equal to the B series, and this is inconsistent or not. I will just put this aside, but the idea is try to check in our physical theories to see if they can capture some element in the theory that allows us to distinguish substantially between a series going from A to C with respect to the series going from C to A, for example. So I would pose the problem in this particular way. It's not mainly related to entropy increasing behaviors. It's not mainly related to an asymmetry between initial and final conditions. This just is a discussion that could come afterwards. The basic problem is, I think, is this one. And then from here, we can start to build up different approaches or different strategies to check where the substantial difference really rely. But so far, I mean, I think this is the basic, the more clear and pure way to start to think about the problem of the arrow of time. So having said that, let's now move on to the particular strategies to solve the problem. The problem of finding this substantial difference between different sort of temporal relationships. And to begin, I think that we can have two different general strategies. Some are more philosophy inclined approaches, and other would be more physics based approaches. I can have this puzzle of the error of time, and I can think that the solution of this issue relies on analyzing conceptually uh, uh, analyzing how our concepts try to capture the idea of time, the idea of direction, or wherever. Or I can rely on how we experience time and how our concepts try to capture this experience of time. And then I can argue that the arc of time is based on these commitments, for example, to change, this commitment to respect with our experience of time, and so on and so forth. This is what I call a philosophy inclined approach, in the sense that we don't need physics to figure out whether there is an arc of time. We need to look into our concepts, into our language, into our experience, and then we can derive or we can extract the arc of time from there. Physics-based approaches obviously take a different strategy in this sense, because there is the assumption that the arc of time is somehow a property of the physical world, that a physical theory can, or maybe cannot, but in principle, we would like to our theory to capture this property of the world. Or probably it's a theoretical requirement in order to formulate our theories to be empirically adequate. For example, we need to postulate an arc of time because otherwise our theory wouldn't be empirically adequate. But I think that these are two different strategies. I think that both of them are equally valid at some point, but it depends on our philosophical tastes, our philosophical guts in some sense. But to give you a better impression of what I'm referring to, for example, if we think of McTaggart's argument or something like this, to reject an arc of time is a clear example of a philosophy inclined approach to time, in particular to time direction. One can say that, well, according to McTaggart, if we analyze carefully this structure, this temporal structure, and then we for some reason come to the conclusion that time should instantiate a C structure, therefore there is no arrow of time because there is no passage of time, there is no way to define earlier or later relationships between different events. This is, for example, one way in which we can conceptually just get rid of the another of time from our metaphysics from our ontology. Again, there's no physics here. Physics is just silent and doesn't play a relevant role in our understanding of the arc of time, in our understanding of time in general. Or we can also, for example, support an arc of time because our way of understand change. For example, if we hold a sort of Leibnizian relationalism, we can deduce that there is or there must be an arc of time if there is something like change. This is how Leibniz understood the nature of change in terms of something that is intrinsically directed. So if it's intrinsically directed, in order to differentiate time from space, then we require that the world, if relationalism is true, well, probably it could be also temporarily directed. I mean, we can obviously discuss and go around this idea, but my main aim is try to give you a possible approach to the arc of time that doesn't need physics to figure out the problem, to formulate the problem, and to offer a solution to the problem. But obviously, this talk will be focused on the physics-based approaches, in the sense that, in the sense that I mentioned before, that we believe that it's not enough to conceptually analyze our language, to conceptually analyze our metaphysics, to draw a direction of time. We need to look into our physical theories. We need to look into the way in which we formulate our theories, and then try to see if we can find a way to get an arrow of time. And now we have this distinction between, for example, local or global arrow of time. This is probably one of, well, it could be, but probably it's one of the main distinction. And the distinction is mainly about this. Whether we have an arrow of time that holds locally, there is in some regions of space-time, in a probably directionless universe, or we have an arrow of time that holds for an entire universe. On the first side, for example, is Boltzmann approach to the arrow of time, because he thought that globally the universe was in a thermal equilibrium, so there was no arrow of time in the universe as a whole, but in some regions for statistical fluctuation, the entropy went down and then went up again. And in this particular region, we can define an arrow of time if we understand that the arrow of time is related to entropy increasing processes. But the idea is that the arrow of time is not something that holds for the entire universe, just for some special regions that meet the right sort of requirement to define an arrow of time. For example, regions in which the entropy increases. Global, people that think that the arrow of time is global, well, obviously think that this is not the case, that the arrow of time holds for entire universe. So it doesn't matter where and when you are, there will be an arrow of time anywhere, in any way. For example, the Penrose Big Bang, Big Crunch approaches is a kind of global arrow of time, since that from the Big Bang on, there is an arrow of time everywhere. And then we have a second difference. One can either be a reductionist about the arrow of time, or one can be a primitivist about the arrow of time. This is two different sides in the discussion. For the reductionist, the temporal features, there is any temporal relation that we can find in our experience or in our language or whatever, must be reduced to some non-temporal feature. For example, some asymmetry in the material happening in the world. For example, entropy increasing processes again, but also could be cosmic radiation or any asymmetry that you can come to find in our physical theories or in the world. But the idea is the first one. Temporal relationship can be reduced to non-temporal relationships. For the primitivist approaches, well, the situation is quite different because the starting point is different. The reduction shouldn't be guaranteed from the beginning, but we should start with the idea that temporal features cannot be reduced to anything else, are somehow primitive, primitive in our ontology, in our metaphysics, and the direction of time would be an intrinsic property of time. So any temporal relation should be explained, should be detailed further in terms of temporal notion, because there is no way to reduce temporal relations or temporal features to non-temporal features. This is just obviously a situation that is pervading in the philosophy in general, but in the particular case of the arrow of time, we can find these two approaches. To give you a better impression of the reductionist approach, probably Reichenbach's definition of the arrow of time is one of the most popular, and that was kind of orthodoxy, at least in the main points in the discussion. Because for Reichenbach, the direction of time is the direction in which entropy increases. It's a definition, like he says. So as this definition, what is reducing any temporal feature to a non-temporal feature. Once again, this non-temporal feature for Riemann is the direction in which entropy increases in most thermodynamical processes in a solid system, and so on and so forth. So their argument the underlying argument for this approach is something like this. We start with our intuitive understanding of time. So we think that time passes by, that flows, blah, blah. So we can define some temporal relationships between different events. A comes always earlier than B, and B always comes later than A, and we can just add more events to this structure and get a sort of linearity going from one point to the other, but never the other way around. So we can define all this in our intuitive understanding of the world. Then the approaches suggest something like this. Now, to explain this temporality, this directionality of time, reduce time to some physical material asymmetry in the world, something that in the world exhibits our asymmetric behavior. Entropy was a very good candidate for this. So this is why the majority of approaches try to reduce, at least at the beginning of the 20th century and the end of the 19th century, reduce temporality and the direction of time to entropy, because it was the right sort of thing that could exhibit the right sort of asymmetry to capture something like time. So then we can define some relationships in terms of this material asymmetry that could be physically correlated, like Sklar says, with the temporal relationships. So far so good. I mean, we have most of the job done for the reductionist approach. But then there were some additional problems, because we start with a temporal structure that we want to reduce to a non-temporal structure, but then this non-temporal structure was reduced to a structure that is classical mechanics, that happens to be completely blind to the direction of time. So we have these evident temporal asymmetries in the world. We find some material asymmetry, but it happened that this material asymmetry was described, or was in turn reduced to a symmetric structure, like, for example, classical mechanics with its time reversal invariant laws. So, and then this was the main problem for the reductionist approach. How may irreversibly processes or temporally asymmetric processes be temporally directed, be temporally asymmetric, if they reduce to a temporally symmetric mechanical process at the end? So if we believe that thermodynamics somehow reduces to classical mechanics, and then we think that the direction of time is given by thermodynamics processes, then we have this problem, because at the end we have a structure that reduces everything that is no longer time asymmetric. So the problem was try to figure out how we can solve this issue. This is the orthodox view, how the problem is usually approaches. Try to find a reconciliation for these opposing worlds, the macroscopic and temporally asymmetric world, and the microscopic and temporally symmetric world. So this is the more or less around roughly the orthodox view of the Earth time. But if there is an orthodoxy, there should be also an heresy. And the heresy came with John Earman and the time direction heresy. And let me quote him in full, because I mean, it's very clear what is the intention, what is the aim of this heresy. The main point is that if there is a temporal orientation, if there is an arrow of time, then the arrow of time or temporal orientation is an intrinsic feature of space-time, which doesn't need to be, cannot be reduced to non-temporal features. And secondly, that existence of a temporal orientation doesn't hinge as crucially on irreversibility as the reductionists would have us believe. So now this heretic approach is put in the discussion upside down, in the sense that there is no need to find a temporal asymmetry to reduce sorry, there is no need to find a material asymmetry to reduce the temporal asymmetry that we find in the world. We have to look for the temporal asymmetry as it could be built in the theories in a non-reductionist way. We have to look for an intrinsic feature of space-time as it's formulated in our best physical theory, and try to find there whether there is a arrow of time or not. But the project of finding a reduction is just hopeless, and it just misses the point, as Irvan says. And also other philosophers have followed this view. For example, Tim Modeling also, even though Tim is not so clear as Irman was about the direction of time, about how to build this structure, he also believes that the time and the passage of time and the direction of time is somehow intrinsic in the structure of the space-time. It's somehow built in the structure of the space-time. So we have to find this feature, and I'm trying to show how this feature can be defined theoretically in terms of our best physical theories. So this is a rough and very superficial presentation of the different view. Could be obviously discussed, and probably there are many others, but the idea to frame for framing our project, I think this is enough, because what we are gonna try to explore in our project is an arrow of time that meets the following properties. First, that the arrow of time is a global feature of the universe. I mean, it's really something that holds for the entire universe as a whole. So we are not localist about the arrow of time. We don't think that the arrow of time can be just defined in regions of space-time, and that in different regions the direction of time could be the opposite. What we like to get is a global arrow of time that it doesn't matter where you are and when you are, the arrow of time is always pointing toward the same direction. But also we like to have a view that is not reductionist, that it doesn't hinge upon non-entropy increasing processes, cosmic radiation, or any material or any asymmetric matter in the world. What we like is to have a primitive arrow of time that is not reduced to anything else, but is an intrinsic feature of space-time, following Ehrman's time direction heresy, for example. But then when we start to look into the possible features that could play this role to be primitive for the direction of time, we are gonna focus on geometric features of the space-time. Because if the arrow of time is a intrinsic feature of the space-time, we hold that these features are geometric in nature. So the geometry of a space-time should show us whether there is a direction of time or not. And this is the main points of our project. And then some further basics. Let me go in this way. We think that the best theoretical field to define this arrow of time is the theory that talk about space-time, talk about time in some sense, even in a bigger structure, but take time as an object of study. And this is general relativity. But general relativity is quite wide, so it's quite varied. There are many different models. So our theoretical field has two sides. First, general relativity as a theoretical framework, but also the different cosmological models that constrain, that try to describe how our universe, what are the features of our universe in particular, and not all the possible universe that we can find within general relativity. So in this sense, this theoretical framework, this general relativity plus our best cosmological model, we hope that they will give us the geometrical structure that we need to define an arrow of time. But also our proposal is in some sense modally weak, in the sense that the arrow of time would be just a contingent feature of our universe. It holds for our universe, but not for other universes compatible with general relativity or partially with our cosmological models. It just happened that our universe meets the right sort of requirements to have an arrow of time. But the theory, the physical theory, the physics in general is also compatible with universes without any arrow of time. And this is perfectly fine with us. I mean, we are aware that we don't want something that the arrow of time is necessary, that it couldn't happen that a space-time doesn't have an arrow of time. We are fine with the idea that could be that there are some space-times or universes without arrow of time, but it happens that our universe does have an arrow of time. And this is fine for us because we want to explain the arrow of time in our universe. If you compare this with, for example, other approaches that are stronger, for example, those relying on non-time universal invariant laws, they usually try to say that the arrow of time is necessary according to the theory. In every model of the theory, there wouldn't be an arrow of time. We are not going that further. We are just modally more moderate in this sense. So what we basically need is first to figure out the geometrical constraints on features that any space-time should meet in order for it to support a global arrow of time. So we can start with a pristine space-time and then to think what kind of structure this space-time needs in order to have defined an arrow of time. This is what the first thing we need. The second thing that we need is take a look at our best cosmological models and see and check if, according to these models, our space-time meets those geometrical requirements, those geometrical features. So we are balancing. We will balance our approach, keeping an eye on both both sources of theoretical information, of theoretical resources to defend this project, this idea of a primitive geometrical and global arrow of time. Well, I already said that. So, and basically the condition of this is what Olimpia and Castanino were working on in some time ago, is that the geometrical conditions seems to be something like this. Some are geometrical requirements that constrain the possible structures that a space-time could have, and also there are others requirements that come more from physics or from empirical observation that just narrow down the different possibilities that we can find in generativity and different models. But this is a general map of what we need to investigate, we need to establish for defending a strong viewpoint about the arrow of time. So let me go run through with these requirements just to give you an impression of what we are going to do in the following years if everything goes right. So the first requirement, suppose that we start with a pristine space-time, completely pristine space-time. So the first thing that we can ask this arrow of time to have in order to define an arrow of time afterwards is that this arrow of time be, this space-time be temporally orientable. And the definition of temporal orientability is this one. Space-time, there is some manifold with some topology plus a metric, is time orientable if there exists a continuous non-vanishing vector field on the variety which is everywhere non-space-like. To give a picture of what this means is that the space-time should be such that it doesn't look like for example, a Moebius band, or it doesn't have some temporally closed curves, for example. The things that you can move you can move your vector field along the variety, but it's always pointing toward the same direction, and never you get the vector field pointing toward the opposite direction you start with. This is basically the idea that temporal orientability try to geometrically capture, and this is quite intuitive why we want this in our space-time in order to define an arrow of time. Otherwise, the arrow of time should be the arrow of time could be pointing towards some direction at some points in the variety, but in the opposite direction at other points in the variety, and then the arrow of time wouldn't be global because it would be pointing toward different direction depending on where and when we are in the space-time. So this should be a reasonable requirement in our space-time for having a arrow of time. Well, I already said this. The second and the third condition are more or less quite related to each other. Probably Olimpia would say something about this because with Castanillo, they were working particularly about this, if we can doing without any of these requirements. But for now, the second thing that we can ask our space-time to have is some global time function. A global time function guarantees that the space-time is globally splittable into hypersurface of simultaneity. This, in turn, defines a foliation of the space-time, a consistent foliation of the space-time. So in order to achieve this, well, they discuss the kind of thing that they need to discard. But the idea is that we should be able to split our space-time in such a way that the global time function always increase monotonically. And this is the definition of this global time function. So this is the second requirement that we ask our space-time to meet. And what this yields is a single time ordering for any event of the universe. As I said before, the value of this of any of the events increases along every future directed non-space-like curve. Then one could ask, and then we can discuss if this is really necessary or not, that the space-time also has a cosmic time. So we need temporal orientability and then a global time function, and also we can ask a cosmic time. This is the definition of the cosmic time. But what basically this means is that give some physical meaning to the global time function. What before was much more formal requirement in order to split the space-time, but now the cosmic time seems to guarantee that all the processes can be coordinated by a single time, like simulating the idea that we have a parameter of the evolution of the universe. Then, as I said before, I think that Olimpia Castanino revised the necessity of this third requirement, probably in a discussion. In a discussion, we can analyze this, but this is one of the general, just the general idea of the sort of thing that we can require our space-time to meet. So taking stock of all this, we start with a Princeton space-time. We require temporal orientability, then we require a global time function, and then we require a cosmic time. And all these conditions, plus some details that we can discuss afterwards, provide the geometrical condition in order for the space-time to have the right sort of the structure to define a temporal orientation. What we are looking for is how in this geometric basis, in a space-time that meets these requirements, we can define a temporal orientation, because so far we only have the structure, but we don't have yet the temporal orientation that plays the role of an arrow of time in a geometrical structure like this space-time. So now we have to find a way to define, or at least to be clear about what a temporal orientation amounts to. And these are two a bit cryptic definition of temporal orientation, of time orientation. But well, I mean, I don't know if I have time, but probably it's better to have the intuitive view, because these two definition of temporal orientation is in terms of a diffeomorphism that fix the hypersurfaces, blah blah blah. All this translate into the idea that in a space-time with a temporal orientation, we have an underlying geometrical structure that doesn't look the same in both temporal or in temporal direction. We can have a temporally orientable space-time with a global time function, also with a cosmic time, but still this structure could be symmetric with respect to both direction in the space-time. So what we need is to break this symmetry by imposing that the space-time could be asymmetric in the sense that it looks different, geometrically different in the future to past direction with respect to the past to future direction. If I am at any place at any time point in the variety, when I see toward the future, I would see a different structure than you would see in the past direction. It is basically what a time the notion of time orientation try to capture, and it's the same concept that the arrow of time try to capture. The Olympia's examples, if we look at an arrow and analyze it geometrically, obviously the direction from one extreme to the other are different. It's not the same to look at the arrow from the tail to the top that from the top to the tail, because there are objects that geometrically look different depending on where we are on the object. So we can think of our universe in this sense. Even though we have all these geometrical requirements met in our space-time, we now require that it looks different in the two temporal directions. And this is the notion that temporal orientation trying to recover. So we need to find a way to say that our universe has a temporal orientation. What a temporal orientation allows us to do? Basically, it allows us to pick a direction in our vector field that is non-arbitrary. So we can define now the time orientation in this particular way. If a space-time is time orientable, also has a cosmic time or a global time function, we can define a continuous non-vanishing non-space-like vector field, blah, blah, because this is what time orientability means. But the idea is that the choice of one of the vector fields, the plus and the minus vector field, is substantially different because they are pointing toward different structure of the space-time. In this case, the red vector field pointing conventionally toward the past is seeing a geometrical structure of the space-time that is different from the structure that the blue vector field is seen when conventionally we define that is pointing toward the future. The word future and past are conventional, but they are based on a substantial difference because they are pointing toward different halves of the space-time that looks different from one point or the other. And this is what allows us to pick a temporal orientation to say that, well, the vector field with plus, the blue vector fields is pointing conventionally toward the future, but what matters here is that it's substantially different to the vector fields, to the minus vector field pointing toward the opposite direction, and is seeing a different sort of structure for the space-time. But what allows us to make this choice in a non-arbitrary way, and what doesn't allow us to swap the vector fields is this geometrical structure of the space-time, that the space-time happens to have an asymmetry. Is this asymmetry what allows us to then pick one of these vector fields and say, well, we say that this is pointing toward the future and this one is pointing toward the past. So the whole yeah, the trick is more or less the following. I am at one point in the space-time, and I have these vector fields. I am in this Lycon structure, and I have some vector fields that are positive and some vector fields that are conventionally defined as negative. So, and if I need to say what is the future direction of time and which is the past direction of time, if I have this underlying geometrical structure, I can easily pick one of these and say that this is pointing toward the future because it's pointing in a direction that looks geometrically different with respect to the opposite direction. And this is the conceptual and also the geometric basis for defining an arrow of time in any situation in which we can be. So this is the geometrical distinction and the substantial distinction between different vector fields. For example, the flow.
Christian, sorry if I interrupt you, but I would like to remind you that it's not that we are running out of time. Of course, we have time but we would like also to have time for the discussions.
Yeah,
know if you can wrap up at some point.
Yeah, I am almost done.
Thank you.
sorry. Well, I think that this is more or less clear what is the idea underlying. So, okay, this is pretty obvious, but we first impose some temporal orientability. Then we say that, okay, the spacetime should have this geometrical structure. And then we suppose a second structure that is like cosmic time. And then we say, well, we need that this space-time also be time asymmetric. And when it's time asymmetric, we can define, we can distinguish between this, for example, vector fields. And then, well, if everything works well with this, then we can define a temporal orientation in the sense that I said before. But now, I mean, I think that I would like to just mention two problems. The problem that I don't know exactly how to figure out. Probably you can help us, or you can also point to different problems. But it seems to be a little bit fishy in our argument how we can go from a time symmetric space-time to a time asymmetric space-time. Something should play the role of transforming a symmetric space-time into an asymmetric space-time geometrically. Some have proposed that non-time reversal invariant laws could play this role, or some fundamental material symmetry in the universe could play this role, but it's not so clear for me. But I mean, this step could be a little bit fishy, but also it's not clear what could happen in a universe with singularities, with black holes. This could be interpreted as a violation of time orientability, and if time orientability is violated, so the arrow of time could be non-global. And this would be a problem for our approach. So you have to think further about, well, how can we hold this approach even though our universe seems to have some singularities? Or our way to understand singularities so far is one in which time orientability seems to be violated. And of course, your worries, objection could fit here, please. So I think that that's all. Thank you for listening.
Okay, thank you very much, Christian. Okay, so are there questions? You can raise your hands. I think, okay, Karl Höfer.
So if I didn't miss something, what gives our universe contingently a direction of time is the fact that it starts in a big bang and doesn't end in a symmetric big crunch. Is that right?
Sorry, I didn't hear the first part because your microphone is a bit noisy. At least I'm. If you can repeat the first part of the question, please.
Yeah, I was asking if the contingent intrinsic asymmetry that you're relying on is the feature of our universe that it starts in a big bang, but does not end in a symmetric big crunch. So basically, you're pointing at the endless expansion of our universe as the feature which makes it possible.
Yeah. Oh, okay. I have a reply, but I think that Olimpia has another reply, so probably Olimpia could go first, and then I give you my reply.
If the universe is Big Bang, Big Chill, or something like this, it's evident that it is asymmetric. But even if you have a Big Bang, a big crunch universe, the symmetry is only regarding the radius of the universe, but the distribution of matter and energy doesn't need to be all the fields in the universe. That means that there are very thin asymmetry, geometrical asymmetries. I mean, you don't have an asymmetry, completely asymmetric, symmetric universe. In fact, as always, complete symmetry, and we can show, and we have shown in our papers, symmetry has zero measure in the space of all possible universes, even considering the Big Bang, Big Crunch, because the only, I mean, the only variable is, I mean, the radius of the universe is not, absolutely not the only variable of the universe. You have many variables, and to make all these variables to be confabulated to make a Big Bang, Big Crunch symmetric universe has zero measure.
Okay, I'm waiting for Cristian to tell me how he was going to answer.
Okay, I will. I mean, in some sense, I can see that the big, I mean, probably what I want to say is not the same that Olimpia says. So probably we have some discussion with Olimpia afterwards. But the point is that, yeah, the Big Bang, a Big Crunch model could be one in which we have some asymmetry that could hold consistently along the universe. I mean, on the whole universe. But in any case, if you want to say that this asymmetry is primitive or is a non-reducible feature of space-time, in the sense that time is itself asymmetric, you need all this structure and to translate this asymmetry in geometrical terms. I mean, because I mean I think that the underlying idea in Ehrman's heresy is that, okay, we can find some material asymmetry like the Big Bang or Big Crunch model, but if this is really an arrow of time, it needs to be somehow encoded into the space-time structure. And the way in which we can encode the arrow of time in a space-time structure is by meeting all these constraints. So I think that conceptually, all these structures come first, and then the Big Bang, Big Crunch model could play an additional role, but you need all these conceptual a background to define a primitive or intrinsic arc of time in a universe. It's not enough with the Big Bang, Big Crunch model. I don't know if this is the right model. I don't know if this is the right, but what I think is that it's not enough if we want to defend something more substantial, or approach that think that the arc of time is intrinsic or is encoded in the space-time following the Urban heresy. So this would be my reply.
Okay, thanks. I have more questions, but I see that Federico has one.
Yeah, well, if it's connected to this one, Carl, you can go ahead. If it's like a follow-up, no? Okay, then Federico.
Okay, thanks. I will be brief because it's a follow-up, and then I will leave the others. So yeah, it's a follow-up on Christian answer. So in general relativity, the structure of space-time always depends on the distribution of matter. So how could you have, as you said, an asymmetry that belongs to time itself, so to speak? So I'm thinking about, for example, the sitter space-times. Do you have a symmetry in such empty universes, or so that does not always come to depend on initial condition and distribution of matter in the end?
Yeah, I mean, I'm not completely sure about my answer, but this would be something like following. Obviously, there will be some models of some universe that can be drawn from general relativity that couldn't be an arc of time. This could be empty universes, or universes filled in some particular way, but where the material is asymmetric. Obviously, what we need is a universe in which this geometrical asymmetry should be reflected in a material asymmetry. This is fine, but then what is playing the role of defining an arc of time is the geometrical asymmetry that is correlated. I mean, obviously this could be philosophically discussed, because some people could be that, okay, the geometry is primary and the material is secondary, or it depends on which view of space-time you have. But it's true that there would be some correlation between the distribution of energy and matter in the space-time and the geometry of the space-time, because it's what general relativity more or less says. But the arc of time is encoded directly in the geometrical part, but also reflected in the material part. But then I think that probably we have to discuss, well, what's the nature of the space-time? If there is really two different things that are correlated, or it is only one, and the other one is, you know, an idealization on the first one, or the other way around, that the material happening is just some emergent thing from a space-time that is substantial. Probably this is a very good discussion to go on in our project. But what you say, I think my first impression is that it's true. But again, what is playing the role of the giving an intrinsic arc of time, an arc of time that is not reduced to anything else, is that it itself encoded in the geometry. In the geometry is the geometry of the space-time, so it's time in some sense. This would be my answer. I don't know if you are happy with that or not.
Yeah, no, I'm happy with all the talk, so that's fine. I mean, I think I will need to grasp a little bit more the technicality behind general relativity to formulate better my doubt. So I will just take your answer.
Yeah, me too. But but I mean, I'm thinking, I mean, because what you just said is interesting in the following sense. It's true that there exists this correlation, and probably Carl can help us here, because it's true that you have this correlation, but then I mean, if you have, I don't know, a super substantival metaphysics of space-time, suppose, then, well, okay, you are committed to something like all there is in your ontology is a space-time. So probably what is the material distribution is not metaphysically relevant as the space-time itself. That is what your ontology is made of. In this sense, time is completely primitive if you can define all this structure, and it doesn't depend on the material happening, on the material, sorry, it doesn't depend on energy and matter distribution, because this is ontologically subsidiary of the super substantival space-time. I don't know. I mean, probably the solution of this question of the point that you have raised relies on trying to explain where your metaphysical commitment with the space-time. What I have said is just an idea. I didn't think through this idea through, but probably someone you have something to say about this.
Okay, thank you.
Alvaro.
Thank you for your talk. It was very interesting. So when you were introducing your project, you said that you wanted the time asymmetry to be something geometric, encoding the geometry of space-time. And then I thought, oh, well, if space-time is well behaved, you won't define an orientation, and there is no problem with that. And then in your slide about time orientability, you said, oh, but we want to have some criteria for this. And then you draw this space-time as a square and this space-time as a triangle, and say, oh, in this kind of space-time, I can have my orientation with some reason for this. But for me, it wasn't clear what was meant by this triangle and this we representing this space-time that was asymmetric. You said that the future looked kind of different, but can you make it some more precise?
Yeah, you mean this idea that you are constraining your space-time with some sort of structure, that time orientability, then a global time function or a cosmic time, and then you have to go with time asymmetric space-time, and this is the path from the square space-time to the triangular space-time. You are referring to this path, right? Yeah, I mean, the honest answer is I don't know. I mean, this is the requirements. You say, okay, I believe that there is an arrow of time. I believe that this arrow of time is global. I believe that this arrow of time is intrinsic. Then I have to go with relativity and try to see the cosmological model and define all these structures. Say, well, this is very reasonable. And our cosmological model suggests that, well, we live in a temporally orientable space-time, blah, blah, blah. Then we need a time asymmetric space-time, geometrically. And then I can define the time orientability. But then, yeah, the fishy step is, well, it seems reasonable to go to say that we have temporal orientability, blah, 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 but this time asymmetry, I'm not completely sure. Yeah. The point is that probably Olimpia has something to say, because she believes that there's an asymmetry. Yeah. So
I mean, I will not pose this problem in terms of passing from something that is symmetric to something that is non-symmetric, asymmetric, because as I answered Carl previously, symmetry is something very special. Normally, you find asymmetry. Symmetry has always, in the space of all the solutions of something, symmetry has always zero measure, because it's very, very special. So this does not mean that the arrow of time is necessary. Of course not. You need a lot of conditions, but even with these conditions, asymmetry is another condition. But now it's not a condition like the past hypothesis or the special initial conditions. No, but because it's a very normal generic solution. The non-generic solution is symmetry. So it's not to pass from one to another, because it's something like thinking that the normal thing is symmetry, and I have to explain asymmetry. And in probabilistic terms, the way is the other direction. Normally, you have asymmetry. Symmetry is very special.
Right. But my question would be, of course, generic spaces in spacetimes in general relativity are asymmetric. You have different things at different times and so on. And you can choose an orientation for spacetime. You can define your vector field according to different criteria. So I don't know, why would we choose one of these to be something special and call it the arrow of time? Oh.
One of the directions,
one of the directions, yeah.
Well, because when we talk about the arrow of time, we are saying, as Price insisted, we are using our anthropomorphic language, and we ought to think about future and past. But the fact is that the only thing we need, like in an arrow, is to make the difference between the two extremes of the object, in this case, the universe. And that's all. Then you can call the extremes future and past, or past and future, or Donald Trump and Joe Biden, or plus and minus. On names are conventional, but the difference between the two halves of the universe is substantial. This is something that cannot be, that does not depend on names. So I insist, find an orientation, a direction of time is not to find the place of the future, because the word future is anthropomorphic and completely conventional. I don't know if
so may I go ahead, or should I let anyone?
Just let me.
Okay, yeah.
So, Fede, you have raised your hand because you have another question. No, it's in automatic. Okay. Carl had other questions, if I'm correct. Carl? Yes.
Yeah,
Okay. Yeah. So I think that.
But Alvaro wanted to follow up, I think.
Yes, if it's a follow-up, then Alvaro continue, and then Carl can make the last question. So, yeah.
So of course, in our universe, there are like 1 million criteria for which we can distinguish the two ends of the universe, as you said. So we can look at the scale factor, we can look at matter, or we can look at whatever we want. But then I think you want to make this a connection with this and the arrow of time in thermodynamics or another branches.
Okay. Okay. Well, this is interesting because this was a part of our original work. Then this was a point that made Hugh Price to Castagnino and me in a congress. And so we tried to extend this, showing that under certain additional condition, in particular, the dominant energy condition, you can transfer, I cannot say that this because it's a little bit technical, but you can transfer this asymmetry to the local regions as an energy flow that points to the same direction in all the space-time. I mean, it's not a vector, it's pseudo-vector, but doesn't matter because it works well in each region of space-time, and it points to the same direction. Which direction? The direction is conventional, but the fact is that if you fix in some space, in some point of the space-time, the direction of this pseudo-vector, energy flow pseudo-vector, that one will point to the same direction all around the space-time. So this connects with the idea that there is something that flows, I mean, a physical magnitude like energy that flows in space-time all to the same direction. I don't want to say future because the same direction.
Okay, thank you.
Carl?
It is very interesting.
So yeah, it's a very nice proposal. I mean, I'm sympathetic in many ways, but in the big literature, the interest in whether there's an arrow of time and how it's connected with physics often has had implicit behind it the idea that if we understood the arrow of time, it would be explanatory of why there are all these time asymmetric phenomena that we observe around us. And your approach is really giving up on that as far as I can see, right?
Our approach is what?
Gives up on any
No.
attempt to make it explanatory of the physical asymmetries in material processes.
No, completely, just because what I answered recently to Alvaro. If you have, we call if you have a time symmetric law, you have always two different solutions, one pointing to one side and to the other side. So we call them time symmetric twins. The point in the local field, in the local regions, is how, when you have a time symmetric law, how do you choose one of the twins and discard the others? Imagine why you choose retarded solutions in electromagnetism and not advanced. Well, when you have in each point of space-time defined an energy flow pointing to one direction, it is pretty easy or reasonable to say, well, I will choose, for instance, retarded solutions because they are the one which carry the energy flow to one direction. And so it's legitimate to take one of the twins and discard the other. This is the way, and this is something that we also explained in one of the papers, how that geometrical symmetry is then transferred to the local points as energy flow, and that energy flow, I mean, space-time energy flow, not a pointing vector, space-time energy flow gives me the tool to retain one of the time symmetric twins and discard the other. And the fact is that since all the energy flow points to the same direction in all the space-time, this selection of the twins is compatible all around the space-time. This is our project. There are problems. There are problems because this needs that, the dominant energy condition needs that matter is positive and normal all around the space-time, and we know that close to singularities you have problems. What happens with black holes or wormholes, and there are many problems. These are, I think, the problems we have to point to now. The idea to transfer to the local field, I think that we have some, we can discuss that, but we offered a solution. Then we can discuss it.
Okay.
In any case, I have a, I agree on what Olimpia says, but I have a different answer because I'm probably going out a limb on here, but it's completely true what you say, Carl, that usually the problem of the error of time seems to explain why we observe or why we have experience of a time asymmetric reality or time asymmetric world or whatever. This is true. But then, I can see the link between what we observe, because when we observe, we are in a world where there are, I don't know, non-conservative forces everywhere, where we have, I know, a lot of things that are going on that are evidently, for example, non-time reversal invariant. The classical mechanics that describe the world as we observe it is non-time reversal invariant. Then you say, well, but at the fundamental level, when you just get rid of non-conservative forces, you idealize the world and say, well, suppose that there are not friction, there is no air in the world, then you say the equation, blah, blah, is time reversal invariant. But this is not the world we live in. The world we observe is a world where this obviously time asymmetric, but the physics that describe this world, this particular world, is also time asymmetric. So I don't see really what is the problem with that. What's the point to say that, well, classical mechanics is time reversal invariant? Well, yeah, it is time reversal invariant, but for some highly idealized models in which, for example, you don't have non-conservative forces. But in our world, there are conservative forces. So why we observe time asymmetric world, well, the physics itself describe very well why we observe that world. That's why I think that I wouldn't say that this is the main project, or this should be a part of the project of the error of time, of solving the error of time, of accounting for the error of time. But again, this is a bit preliminary, and I'm not completely sure about this. But I don't see the necessity to try to explain even physically why we observe what we observe, because what we observe is quite complex, and in that complexity, obviously obviously the direction of time is there, is evidently there, even if you look at physics.
Yeah, that's good.
Okay, if there are no other questions, I would like to thank our speakers.
Can I say something final? Well, thank you everybody for hearing us, and I would like to say, Carl, thank you especially, because he's a specialist in this matter of space-time, and that I would like to send you, Carl, some papers, so we would be very proud to hear your impressions, because it's something that I made some time ago, and I would like to hear your opinions, because I think that your opinions will help us to continue to develop the opinions and criticism and all that. to continue to develop this project. We are beginning again with the new.
Okay, that sounds very good. Thanks.
No, thank you.
Yeah, I would like to thank you of you for hearing me and for hearing us and for all your comments. It was very helpful. So thank you for inviting us again.
Thank you. So have a nice day. You're in Argentina.
Yeah.
So
Yeah.
and to the other people, have a nice evening and
Evening.
soon to I mean, see you soon in our next meetings. Bye bye.
Bye bye. Thanks
for coming.
Bye-bye.
Bye.